information, the quantity of information that is carried about a random variable once the other one is measured. There is also a possibility of drawing a diagram in which these quantities are combined to show why these quantities are equal to each other. So this is just picturing classical information theory. Let me go to the quantum counterpart. We change random variables x and y with states, with density matrices. I will call the total density matrix of the system rho, and this is equal to just the rho AB. And we have also the density matrix of the subparties. The density matrix of the part A is just obtained by tracing out the degree of freedom B, and the density matrix of B is obtained by tracing out A. And instead of using the Shannon entropy, we will use the von Neumann entropy, which is defined as the minus the trace of the rho log rho. The main difference between quantum and classical information theory with respect to the description of nuclear information is that in quantum theory in general, base rules do not apply, are not valid. This means that if we start from the definition of I and try to quantize it, we find different non-equivalent quantum analogs. We find, for instance, if we apply directly to the, we change this expression, the Shannon entropies with the von Neumann entropies, we obtain this relation between S of rho A plus S of rho B minus the total Shannon entropy. And if we take one of these ones, the first one, for instance, we obtain another quantity, which is the difference between the Shannon entropy of one party minus the conditional Shannon entropy. Now, these are different, and furthermore, this quantity depends on the specific measurement you realize on the party B.
And how have you defined rho A conditioned by B?
I just quantize this expression. I will have the sum over P of S over. I will try to write it. The sum of a number of elements of the measurement I, Pi for S of rho A given B equal to I.
No, but I don't understand what do you mean by rho A conditioned by B?
You measure the party B and you are tracing a degree of freedom. You have rho. You measure this object on B and you obtain rho A given B equal to I. And you sum over all the possible results of tabular elements of the measurement.
But is this different from the trace over B of rho?
Yes. Because here you are extracting this number, so you must normalize. So if you want to trace, you have just the trace of rho. B of rho is just the sum over I of I rho I. Sorry.
Yes, this is the line above.
Yeah. No, I'm saying that this is the entropy of each of the results.
Okay.
The sum with entropy.
Before summing up,
yeah,
you make the entropy of each individual.
Yeah. The two conditions are not commute.
Rho of A condition to be equal I is acting on the same space of total rho.
No, this is acting. This is only acting on A. is the probability of having a density matrix in the party A given a result of a measurement realized on obtained in the party B.
Like maybe in some different version you can put it as project or left and right of total.
Yes. Okay.
So you fix the subsystem B in a given pure state.
Actually, the problem is a little bit complicated because this measure could be realized by using non-orthogonal objects, but it's not necessary that the measure is made with the projectors. In just a sub-case, you could find just a bound on the quantity it produces. Okay, I just say that there are two classical objects describing the nuclear information that in the quantum scenario are not identical. Zurek and Oliver define as the quantum part of the correlation of the system the difference between these two objects. I have I, just the difference between the density matrices, the Shannon entropies. J is the quantity obtained by measuring B and maximized overall the possible measurement I could invent on the party B. This J should represent the classical part of the correlations. The difference between I and J is called in the literature quantum distorted and measures the degree of quantumness of a state, of a bipartite state. There is an alternative point of view to describe this quantities I just introduced, I, J, and their difference B, related to the use of the relative entropy between two states. The relative entropy between a state A and the state B is just a trace of A log A minus B log A. It has been shown in this paper that the quantum model information I is just equal to the Shannon to the relative entropy between the initial state, the state total state we consider rho, with respect to the closest state to rho that can be written as the product of a part of A and a part of B. And it has been found that this state is just realized with the marginals, with the parts obtained by tracing out one of the degrees of freedom. This rho A is exactly a trace over B of rho, but this is the trace over A of rho. And also the classical correlation can be described as the relative entropy between the closest state to rho which has not quantum correlations, and the state close to chi of rho, which is a product. I'm introducing this definition because when I will go to the multipartite case, I will need them to justify the quantities I want to introduce.
Gianluca, I'm sorry this is too trivial, but I have a fundamental difficulty.
Yeah.
In the classical definition, A and B are two variables of the same system. And here I and B are two subsystems of a given system.
But also in the classical world you can imagine...
No, in the classical world you have two variables.
Yeah.
And then you find correlations or mutual information.
Yeah.
And those are two variables associated with the same physical system.
But not always. You also have two systems, two lasers, and then you look at the information.
Well, that's how you define your system. You could couple systems and not a big system, and then you got correlations or mutual entropy.
But here is
part of your system.
But here in the quantum version, A and B are just subsystems.
But in the classical
In
Hutton,
the other case, they are variables.
but they could be
In the
subsystems as
classical
well.
case, we agree there can be both things.
No, they are variables. They are variables, not systems.
But can also be two variables or two subsystems. In general, yeah.
Oh, yes. In many cases, Maxim, the classical theory, there are also two systems. You calculate the correlation of the mutual entropy between, I don't know, such variable of system A and such variable of system B. And there are two systems that...
Yes, but there are correlations between two quantities.
Yes, two measurables, two observables of two different
systems. And here is the whole system, is the density matrix of the subsystem. So those are two very different things.
Yeah, it is true that when you calculate the classical entropy, you only consider the probability distribution of the variable of the observable x. You don't consider what are the other variables.
Summing over y.
No. But imagine that the system A is described by x, x prime, x second, x of the vector x, x1, x2, and system B, y1, y2, y2. And when you calculate, you only consider these internal variables. You don't take care, and you only use x and y, and you don't take care of the internal variables for that.
If you have two quantities x and y, and you have, I don't know, x1, x2, y1, y2, which is the probability of p of y1, if you consider the whole system? It would be the sum of the probability of y1 and x1 plus the sum of the probability of y1 and x2. This is the analog of the trace in quantum.
Yeah, but in classic, you trace over all the variables that you don't care, and here you still use all the density matrix for the system. You trace, you do take the density matrix of the whole system, and now you have two subsystems, but then you might trace for part of this, for B or for A, but for A you take all the density matrix, not trace it over many degrees of freedom. I just consider 1 degree of freedom, how this degree of freedom correlates with that other degree of freedom. But in classical, usually you do that. You forget, your system might be 3 variables here, 3 there. You take 1 variable here, whatever, and 1 here, and you compare these two and disregard the other ones in many cases.
That's why in classical information there are base rules and they are not valid. You cannot do.
So it's a more deeper analysis, because besides being quantum, you also really look at all the degrees of freedom of the system, not just one single observable.
I don't agree. I mean, you're saying that in classical you have a variable, you could have other variables with the same probability distribution which is given by the object. For example, position, momentum, or whatever.
But usually you only look at numbers.
When you say x is a variable, in the classical case, what you are taking is the probability distribution of that variable.
Yes.
It's a collection of p and
Yes, but usually
same thing as in one.
yes, but usually you don't. But usually you don't look at all the variables. So you have your system, classical system that has defined by 20 variables, and you only measure 1. And for this other, you measure 1 and look at the correlation of these 2, and disregard what happened with other 19.
But who says that all variables?
It's the same.
You could do it, but usually in classical system, you measure the correlation of one variable of the system against that variable of the other system, not the whole.
If you will also use a speed that has only one variable.
Yes, I mean, you could do it, but in principle, the
This one you can do both in both cases.
yes, but
When you write a state of a system, you are specifying a Hilbert state. Then you are specifying some of the properties of the state you want to decide.
As I see it, if you were to make a fair comparison, then in the classical case, you could say, for instance, my system is defined in phase space, and then the equivalent of rho is the probability density in that phase space. And then I look at correlations between the probability, this probability density in phase space of a subsystem A and a subsystem B. But what you've shown is just 2 variables of this classical system that can be whatever and unrelated to the full state in the classical space. I mean, for me, conceptually, are two things that I don't see that one can compare.
But the origin, you are criticizing the correspondence between the Shannon entropy and the von Neumann entropy, because it's already there, the problem.
No, I mean, if your variable
Yes,
x,
because in the Shannon entropy we have already defined the set of probabilities associated to a variable defined in the state, while in the von Neumann entropy we have the row, the whole row. So this is typically the way in
yeah, but if your
the
variable,
analogy.
if your variable classical x, where the position in phase space, x vector meaning x1, x2, x3, p1, p2, p3, whatever, then is the corollary. And this p of x is the density probability in phase space, and p of xy is the density probability in the joint phase space of the two systems. The only thing is that usually you don't look at all the you don't look at all the variables in phase space. You only look at one single or two variables of the system. But it's a matter of what you. So here you should trace. If you're going to look for several, you should trace for all the other degrees of freedom.
So an important property of the quantum discord and of the classical cooperation is that they are not symmetric with respect to the exchange of the parties. If you measure the party A, you can modify the system in a way different from the way you can modify the system by measuring the party B. This means that these two quantities are in general different. In general, D is not symmetric and J is not symmetric. A way I will use later to symmetrize is just to take the minimum between the two values of the discord and the maximum between the two values of the classical correlations.
How you can measure the discord? You can. I mean,
for instance, if you have two spins and you want to qubits, you can think about the possibility of observing the direction of the spin of one of the particles. And you can measure, if you want to limit yourself to orthogonal measurement, you can project over all the possible orthogonal projectors in two-dimensional space.
Try to
write
all the components for the density matrix, and then from that you infer the discord.
Yeah, you minimize over all the possible measurement and you obtain the discord. So I was saying that in the case of Q states, actually it is easy to show that discord is symmetric, J is symmetric, and they are equal to each other, and they are also equal to the entanglement between the parts A and B. So I say at the beginning that up to 10 years ago, entanglement was considered as the only indicator of quantumness of a system. And then people started to think about other quantities. On the base of this change of opinion is the observation that there are computed tasks achieving a speed up of the operation that can be only justified invoking quantum mechanics that can be obtained by using states that are not entangled. And in 2008, it has been shown that the reason why it is possible to achieve this quantum speed up of computation is the presence in the states of quantum discord. It has been realized that the discord is the essential ingredient to observe quantum effects in computational tasks.
But you said that quantum discord is equivalent to entanglement for two states.
Yeah, for two states. But we try, I try to in 2 slides, I have some quantitative result about it. A state is not entangled, is factorized. If it can be written as the common sum of some probabilities pi I multiplied by the factorization between a density matrix in A and another density matrix in B. This is the definition of a state which is not entangled. Actually, if the rho I A or rho IB are not orthogonal with each other, if you measure one of the parties, you disturb the whole system. Then it means that the state cannot be considered as a classical state. In classical physics, you cannot disturb a system by measuring another one. So the paradigm of classical state should be recast in this form. A state is classical if it can be written as the sum of orthogonal projectors on the part A, factorized by a sum of orthogonal projectors on the part B. There are also, you can also build some intermediate situation where one of the parties is orthogonal, the other is not, and in this case we have a state quantum classical. It's quantum if you measure one party, one classical if you measure the other one. Some stupid trivial examples of different degrees of correlation. The state is completely uncorrelated. It's just a product of a state for A and another state for B. The state is classical because there are correlations. You know that a result of the measure of the first object is equal to the result of the measure of the second object, but correlations are fully classical. A quantum classical state of this form, for instance, the second is orthogonal. We have two orthogonal states, 0 and 1, and the first is not. Here I put 0 and here I put plus, which is the sum of 0 plus 1, for instance, an object and a non-orthogonal object. This is just the maximally entangled state, which is full quantum. So I start to speak about the differences between discord and entanglement. Here, actually Fernando generated 10 to the 8 random density matrices for the Hilbert space of 2 qubits of 2-level systems. And for each state, we measure both quantum and classical correlations and entanglement. The main question we addressed was which are the states, which family of states maximize discord, is more quantum, for a fixed value of the classical part of the correlation, or equivalently, or the total correlation of the system. And we call these extreme states maximally discordant mixed states, and we found an analytical formula for describing it. And then we try to observe the behavior of these states when observing the behavior of entanglement against classical correlations. So we found for these states an analytical expression by starting from an ansatz and then by optimizing the parameters using the Lagrange multipliers, and we found that there are 3 branches. One of them is rank 2, 2 of them are rank 3, and then we put these branches, these extreme branches, these 3 red, green, and black branches, in the same plot where here we have entanglement instead of disorder. For all the 10 to the 8 states, we plot entanglement against classical correlations. We found that one of these branches, the black branch, the rank 2 branch, is not maximally entangled because there are states beyond the line, but is close to the maximum. While the 2 rank 3 branches, red and green, are factorized. This means that for a given range of classical correlations, states with a maximum amount of discord are factorized at 0 entanglement. It is a strike contrast between the 2 quantifiers. They can be really inequivalent. Another way of observing this inequivalence is that here we are plotting, since we generated all these states, we plotted the probability of observing a given number for the discord, for the classical correlation, and for entanglement. And while there are no states, or the states with 0 entanglement, or 0 discord, or 0 classical correlation, have measure 0, it's practically impossible to find from a random generation states with 0 disorder. There is a high number of states which have 0 entanglement, which are factorized. These 2 points just to remark the difference between the 2 indicators. So let me start to describe the case of more than 2 parties. The analog of the mutual information for 3 or more parties is just that's called total correlation, and is given by the sum over the single subparties Shannon entropies minus the Shannon entropy of the total system. The goal of our work was to divide this T as the sum of a contribution called Tn, which cannot be described, cannot be found by considering any of the possible subsystems. It is really n-partite genuine contribution, and other things that I don't want to specify. Just to find the value of the correlation which are really n-partite, if any the number of partitions of the state. So, as I said before, I want to invoke the relative entropy to find a definition of the n. From now on, I will speak about only tripartite, 3 parts, 1, 2, 3, and only at the end I will give some more general result for more than 3 parties. T3 in this case, we define T3 as the distance between ρ and the closed state which has not a tripartite correlation. A state without tripartite correlation is a state which is factorized at least along one of the paths you can realize on the system. You can cut the third element, the second, or the first. And T3 is the minimum between these 3 relative entropes. The distance of ρ with respect to the state with not tripartite correlations. We show that this T3 is just equal to the difference between the total correlation and the maximum between the 3 possible mutual information between AB, AC, or DC. Or, in other words, T3 is the minimum between the mutual information between 2 parts and the third one. This result seems a little bit technical, but it's very important because allows us to apply all the things known for bipartite cases to calculate this T3, because it's just a bipartite object, even if it's describing a multipartite effect. Then genuine correlation are equal to the minimum bipartite mutual information present in the system. This is the next slide. As I said, this allows to divide T3 into its quantum part, D3, and the J3, the classical part, just applying all the things I wrote for the case of 2 parts. It's just to extend one part to call AB just so A prime, and to study the correlation between A prime and C. We are reducing the level of difficulty of the problem. And for 2 states, the result is very simple, because D3 and J3 are equal to the minimum of the 3 possible Shannon entropies of the subparties. On the other hand, since we have defined T3 as, since T3 is the difference between the total T and the maximum among the 3 mutual information of the partitions, we also want to find that D3 is equal to the total D minus the maximum between the discord of the 3 subparties, and the same for J. To do it, first of all, we need to define what is the total quantum discord and what is the total classical correlation of the system. So let's come back to the classical information theory. Now we consider three variables, and the total information is given by the product of the p of the three variables divided by the logarithm of the ratio between the joint probability and the three individual probabilities. Here the base rules allows one to cut this joint probability into three objects. We have I given j and k, j given k and k. And since we have three indices, we have 6 possible combinations analogs of p, I, j, k, and 6 equivalent definition of I in terms of Shannon entropies and conditional entropies. Once we go to the quantum world, we find 6 inequivalent quantum to the quantum Newton information. And if we use the symmetrization criterion like in the bipartite case, we just define the classical correlation of rho as the maximum between the 6 combinations of these quantities, which is just obtained by replacing p with the base roots and then by quantizing the system. So this is also here we have measurement, so this object should be optimized with respect to the measure, here to I, here to j and I. And if we maximize with respect to the indices and maximize with respect to the measurement, we find the total classical correlation of the system. And the discord, the quantum classical correlation will be just the difference between the total correlation and the classical part. Now to conclude our framework, we need to show that D3 and J3 coincide, the two different definitions of D3 and J3, this one and this one are equal. We need true proof that if we fix, we have a system such that the mutual information between I and J is greater than the other two mutual informations, then the same hierarchy is found also for the classical part, J, and for the quantum part, D. We prove that this is true for the case of 3 qubits. In general, there are no analytical instruments to prove it, even if these results seem to be reasonable, we are not able to prove it in general. And if you want to consider other systems, you should calculate by hand these objects and verify that the definition coincides. But there is no general recipe to establish it. There are two, in the case of 2 qubits, where we have a complete framework of definitions. We can play with this indicator to calculate these quantities for some special states. For instance, I wrote the two extremal states. This is the Greenberg-Zaringer state, which is just the maximal entangled state. In the case of T qubits, is the sum of 0, 0, 0 plus 1, 1, 1. And this is the most correlated state I can invent. The total correlations are equal to 3. 3 is the maximum because we have SA plus SB plus SC minus S. In this case, we are saturating the maximum for every component. SA is equal to 1, SB is equal to 1, SC is equal to 1, and S, the total S is 0. Then this state saturates the maximum possible total information of the system. This is distributed. We have 1 bit of classical correlations, 1 bit of quantum genuine correlation, and 1 bit of classical genuine correlation. This state is the most correlated state, but is not the most quantum in a way, because this state called W state, which is just the superposition of states with an excitation in different places, is less correlated as measured by T. By the total information 2.55, but the sum of the two body quantum correlation and three-body quantum correlation is greater than 1. The state is less correlated as a general picture, but it's more quantum in a way. I think this result cannot be obtained by considering entanglement as an indicator of quantities or quantumness of the system. So to conclude, I try to go beyond the case of 3 objects to n, and the first definition based on the relative entropy at a distance can be applied as well. We can define also in a generic case the general correlation as the distance of the initial state with the closest state without n-partite correlation. For instance, in the case of 4 objects, I will need to consider the following cuts: 1 with the other 3, 2 with the other 3, 3 with the other 3, 4 with the other 3, but also cuts of 1, 2 with 3, 4, of 1, 3 with 2, 4, and 1, 4 with 2, 3. Obviously, the number of things to be considered grows with n, and the calculation can be cumbersome. But the result is simple because dn and jn are equal to half of the total general correlation and are equal to the minimum of the possible Shannon entropies of all the objects, the subparticles you can find in your system. So I think this is the last point of my talk. I want to conclude by saying that I introduced the quantum discord as a concept of measure of quantumness of a system beyond entanglement. There are effects that are not catched by entanglement but are catched by discord. We found a Fleming state that make evident the difference between entanglement and discord. And finally, I try to extend the measure of correlation to multipartite system, mainly with the main interest in the measure of genuine correlations. So this is a list of publications on this subject. There are 4 publications exactly on the theme on Discord, and 2 other publications where we use Discord to describe some dynamical evolution of physical system, or system of 2 oscillators coupled to thermal baths. Okay.
Thank you, Gianluca. Questions?
Why do you symmetrize the multipartite classical relations if the bipartite is asymmetric?
Sorry?
Why the multipartite definitions are symmetric or are symmetrized under this permutation of the possibilities, while in the bipartite case you have a asymmetric definition?
No, sorry. I can here I can obtain 6 different definitions of J depending on the measure, the order of measure of the system. That's like
You take the maximum.
I take the maximum. Also in the bipartite case here,
In the bipartite case you take the maximum over measuring always in the same part in different measurements.
no, the principle is this one. First of all, I take the minimum in this case of the 2 measurements, and then I take the minimum between the 2 minima.
Yeah, but this is not what is typical.
Okay. It's a way of
Why should you need to symmetrize in the case of multipartite? Why do you need this?
because I need just a definition of the Intanglement. I cannot deal with more than one definition if I want to prove this hierarchy of correlation I wrote here. This is true if I take the maximum among J and the minimum among the discord.
I have a question. If I understood it correctly, the property of discord is much easier to obtain for n-partite systems than, for example, entanglement, right? And you mentioned in the beginning that the relationship also with quantum computation. With entanglement, it's clear how it can be utilized in terms of quantum algorithms, for example. Is it possible to sketch briefly how Discord can be utilized in a similar way?
Well, I'm not expecting quantum computation, but I want to say that I cited the paper. Two papers actually. These papers. Here, they prove that if you start from a system initialized in this way, 0, 0, 0. No, so, and you attach, you have for say n minus 1 part a completely classical state, a factorized state, and you attach it. No, sorry, I don't remember. I could say some.
I'd be interested in the reference.
Any other questions?
You said that correlation are distant. Can you explain this a little bit more?
So first I define the correlation in this way. I say I is equal to the difference between S of rho A plus S of rho B minus S, the total S. Then alternatively I could say I want to know the difference between the relative entropy. It's not exactly distance quantity because it's not symmetric under the exchange of the two elements, but let me call it distance. To a product state, I want to say which is the distance. I build all the product state possible, the possible product state in my hyperspace, and I look for the minimum value of this relative entropy. And I find that this minimum value coincides with I. So I is equal to the distance between your state and the closest product state. And you could repeat the same procedure for the classical populations and also for the Discord. Actually, the Discord is more complicated because the result would be the sum of two relative entropies. Not exactly, you cannot find just one state, but there is a way of defining it through distances.
I think entanglement is normally mentioned to be connected to non-locality of quantum systems. Discord is also similar to...
No, you can find states that don't violate Bell inequalities, for instance, but they have non-zero Discord. There is no relation between Discord and locality. You can have quantum effects without having no locality in the problem.
It's not the non-locality property that the thing that you use to implement this quantum computation protocols?
It depends on the protocols.
But the more well-known protocols?
Yes, for instance, the short many things rely on entanglement, but there are things that can be obtained also without need of.
So, the question in other words, is any advantage of using an entangled state or the state which is stronger than rather just a state that just has Discord, only that for quantum computations? I mean, is anything that you could do using an entangled or a state that is or that fulfills the FDR paradox that you cannot do it with Discord?
Actually, if a state is entangled, it has non-zero Discord.
No, I mean, but is anything that you could do? I mean, you said you could do quantum computation with any state which has Discord.
Yeah.
So if you go to a state which is deeper correlated, like if it's entangled, can you do anything else, or you can do the same?
It's not known.
No.
And typically, quantum computation is done with pure states. If you go to mixed states, I don't have a picture here. And it's taking many more years people studying the algorithm. And the Discord is only known to give a speed up for certain specific tasks. For example, taking the trace of a Hermitian matrix. And this procedure doesn't have an overhead if you augment the size of the matrix, which classically would have.
So that process, for example, would be the same where the system is just with Discord or this fully embedded?
I don't recall any paper doing this. And the complexity classes of the computation are not clear yet. So you cannot say whether there is a more speed method or some other problem.
And teleportation?
I don't know what is the standard of teleportation with mixed states. They are pure states but judging by the possible locality of a state with a smaller number, maybe for teleportation is better.
Yeah. So if not, let's thank Gianluca. You mentioned that